Okay, so in this video I'll be explaining the general equation for alpha decay. In tutorial 6.1 nuclear medicine you were introduced to a few key things that are going to be important to recall now. So remember from back then, the classical representation of the nucleus is a dense grouping of protons and neutrons defined by four mathematical terms. These four terms you should be remembering by now is X, Z, N, and A. X is the chemical symbol of the element. Z is the number of protons. And remember, the number of protons is what defines the element. N is the number of neutrons. And A equals the total number of nucleons. And if you remember again from last topic, nucleons is the neutrons plus the protons. Now, a common representation of the nucleus is A, Z, X. Looking up from above, X would be the chemical symbol, Z, the number of protons, N, not in this one, A, number of nucleons. N can actually be determined by A plus Z will give us N. Okay, so let's just have a look at an example of an element. So let's just take, for example, magnesium 2512 Mg. So down the bottom here we have the number of protons. We then have the mass number up here and the chemical symbol. Now what we can actually take from this is that the magnesium element that we have here, you should be able to determine that that element has 13 neutrons by simply doing 12 plus 13 gives us our mass of 25, knowing that in this number the A is the number of nucleons, which is of course the number of protons plus the number of neutrons. Okay, just let me clear the screen here and then we'll get into looking at the general equation for alpha decay. So the general equation for an alpha decay is given by AZX goes to A minus 4 Z minus 2Y plus 4,2 alpha. So just to unpack that a little bit, when we have alpha decay, an alpha particle is given off, right? So here we have our alpha particle. Now both sides of this equation need to be balanced. Like in any equation, both sides need to be balanced. So essentially we're saying that an alpha particle has 2 protons, 4 nucleons. They need to come off of here. We have A minus 4, A minus 4, Z minus 2. You take away this 4 and this 2, we get our alpha particle, and we know that we're going to have a new element because the number of protons changes in this equation from Z to Z minus 2. That Z minus 2 is going to tell us what our new element is. The mass number is going to be whatever the mass number was previously minus 4 as we have over here. Okay, so just to put it into a little bit of a context, say we have 22688 radium undergoes alpha decay. We know that we're going to end up with an alpha particle, mass number 4, 2 protons. Now you can work backwards whichever way you want to do with this one, but what we know we're going to end up with on this side is Z minus 2, 86, and the mass number is going to be 226 minus 4, 222. Now, if you want to have a look at a periodic table just to confirm at this point, this is where if you get asked a question in this form, this is where you'll need to have a look at a periodic table. But you'll go to the periodic table, look at what has a proton or atomic number of 86, and in this case it's radon, and it's as simple as that. We've now used the general equation for an alpha decay to show what happens to radium when it undergoes alpha decay.